Can you see the screen?
Yes, sir.
And please call me if there is any internet issue.
Okay, sir.
Okay, so we'll start out today with water quality as we have already completed. I know that remote sensing and GIS is very useful for delineation and mapping of identification of various kinds of water quality, water identification, sediments. So monitoring of water is essential in order to characterize water and identify changes or trend in the water quality over time. So, remote sensing and GIS, because of its multi-temporal characteristics, is very helpful in providing the spatio-temporal characteristics of water, whether in terms of volume, whether in terms of water quality, or to be able to respond to emerging water quality problems like identification of sediments, plumes, harmful algae, all those kinds of study which were previously a field-based experiment is now can be done in your system, can be done using various softwares. You can do with the help of various statistical tool. Yeah, you cannot substitute the field-based data observations and their laboratory analysis. We cannot deny that, but still we have got overall understanding of the area can be known, or nearly 80 to 90% of accuracy can be achieved using various data sets. So satellite based remote sensing is recognized as a reliable and cost effective technique for describing and quantifying the aspects of marine water quality, especially if you go for the oceans, coral, mangroves, for then exploration, marine ecosystem, bathymetry analysis. For such kind of studies, remote sensing and GIS provides you very basic and a good database for creation of those features, and you can easily map those features. So using near real-time satellite data in operational mode, it is equally possible to derive the current environmental situation on both local and regional level. So whatever understanding that we are looking into can be dealt with at a local and regional level. So with a web-based solution, up-to-date information can be made available with only few hours delay. So with we have already, as we know how the database are created, how the data are interlinked in spatial database modeling, and how you will be creating WebGIS. So all the data sets, what you are maintaining it, whether that is pertaining to volume, water quality, can be directly uploaded in the web portal where a user can use it according to his or her requirement. So whenever we are talking about water quality, there must be a parameter to decide which water quality is good, which water quality is bad. So what is that standard, what is the method? So we have differentiated or divided the water quality parameters into three components. One is physical parameters, other one is chemical parameters, and third one is biological parameters. So under physical parameters have been further subdivided into pH, temperature, dissolved oxygen, turbidity, depth, specific conductivity. So physical parameters, we will be calculating pH, temperature, dissolved, turbidity, depth, specific conductivity. When it comes to chemical parameter, what are the chemical elements containing in water? They are concentration of silicate. What is the total concentration of silicate? Nitrate, ammonium, total nitrogen, and total phosphorus. So whenever we are concentrating on chemical parameters, we have to calculate this features, their readings has to be verified in the field. And when it comes to biological parameters, it is chlorophyll, dissolved oxygen matter, and suspended particulate matter. So these are the various materials that has to be evaluated, that has to be analyzed in order to have a basic understanding of that area or terrain. So optically active constituents of water that interact with the light and changes the energy spectrum of reflected solar radiation. So what are those parameters on the basis of which the satellite signature changes? Firstly, chlorophyll, that is very active, unit milligram per liter. Then you have got depth as DD, that is active temperature, color dissolved oxygen, total organic dissolved oxygen carbon, TDS, turbidity, total phosphate. So all this water quality parameter has to be qualitative, has to be quantitatively measured using satellite remote sensing. So remote sensing of water, what does it has got the limitation? It has got the limitation that large number of inland water bodies are available in India, which involves high cost travel analysis of the sample size not representative of entire water body. So these are the some limitation that the remote sensing doesn't have those limitation, or on the other hand the remote sensing is advantageous, like the number of inland water bodies like ponds, dams, stacks, rivers, tributaries, they are so large in number that if I tell or send 20, 30, 40,000 people to cover the entire area, see the area, calculate the volume, it is not physically possible because many of the terrain is inaccessible. You cannot go, you cannot calculate the total volume. Approachability is different. Even if the approachability is it's okay, but it is time consuming. But when it comes to satellite images, because it has got a synoptic overview, so a large area can be calculated, can be viewed, can be mapped, can be monitored, can be analyzed easily. So if you compare the cost of the manpower that will be involved for traveling, for collecting the water, for going into the field and testing it, it is a lot of time taking. It's lot of manpower is involved, lot of money is involved, lot of time is wasted. Instead of that, we'll be making or downloading the various satellite images and we'll be running the various indices models which are inbuilt, or will customize few models for identification of those water contamination zone, and that can lead and that can save time, money, each and everything. And at last, whenever you're going into the field, you cannot go to each and every sample size, but when you comes to satellite remote sensing, each and every parcel of land can be viewed easily, and we can have a sample size from each and every parcel of land according to the desire, according to the objective. So that's why remote sensing and GIS has nowadays been popularly used in all the water quality related mapping and monitoring exercises. So remote sensing has the ability to frequently and efficiently monitor the water quality in inland water bodies. So because of the synoptic, inaccessible, multidisciplinary, time saving, and the other advantage of what we have in a satellite image is a spatial resolution, that it can differentiate the minor differences between the various earth objects, earth features, whether that is within water, that is above water, that is below water, whether that is surrounding the water body, that is overlaying the water. All such features can be easily handled using the spectral data, using the spatial resolution. And if you want to see the changes what has happened in any water body or any river system or any ponds, tanks, lakes, reservoir, you can use the multi-temporal data sets to see the expansion, that whether the volume of water is same or it has decreased. So remote sensing and GIS plays a very important role in the identification, mapping, and monitoring of this river water body. So you can see that the electromagnetic radiation is reflecting back, is coming to the earth surface, and then it's reflected back from the different terrain, like from soil, from sea surface, from atmosphere, from water, from soil, from agriculture. Means each and every object has got a different spectral response curve depending upon the property of the earth material, and that will behave differently in different spectral channels, and those behaviors, those understanding of the terrain must be of a very high standard, so that when it comes to interpretation, when it comes to identification, when it comes to delineation of the various earth objects, we can easily identify those earth objects. So you can see how the reflectance behavior of different water variate according to the graph. So you can see what is the case one is a water with concentration of phytoplanktons is high compared to not biogenic particles. Case 2 are the water concentration of non-geonic particles high to phytoplanktons. So if you see that if the phytoplanktons is very high, the amount of respectance in the infrared band towards the vegetation is on a higher side, and if you compare that with the non-vegetated portion, that portion is very low. So what are the different water quality retrieval methods that we are using or that will be employing in our research? The one is empirical approach, second one is analytical approach. Empirical and analytical. So what do you mean by empirical approach? It is determined through statistical relationship between measured spectral properties versus measured water quality parameter. The coefficient contained in these algorithms are generally divided or derived by pooling data collected at various spatial and temporal scale. Analytical approach, what we do, we accounts for variability in IOPs over space and time, solved through various radioactive transfer models, and a physics based inversion method is developed for estimating water quality parameters. So what are the formula and the approaches that we'll be applying for the water quality retrieval using empirical approach? For open ocean, case 1, water mostly used is empirical algorithm, and the formula for OC2 algorithm is where R is equal to log 10 RS 490 by RS 555, and the cumulative value equal 10 a0 plus a1 r plus a2 r square plus a3 r cube plus a4 r4. So this all are the coefficients are statistically determined using various in situ measurements all over the world. So these are generally those methods where we go into the field, we collect the data sets, we send into the laboratory, and on the basis of various physical parameters, various analytical parameters, those coefficients are calculated, and then we'll be using some formula in order to understand its turbidity level, its chlorophyll level, and its other properties. So using satellite remote sensing, you see this is a part of Ganga that has been properly mosaic to adjacent image where mosaic, and you can see the how large area the satellite image can view at a single point of time, and we can see the exact spatial coverage of the water body, the riverine sands, the settlement area, the scrub lands in between, some plantation agriculture. So all the features are easily viewed when we are taking satellite images. So that provides you very standard living. So in the same way, you can see related to the groundwater quality here, these are the zones where the algae patterns or the contamination zones are very high, and towards the blue the contamination zone or the levels are less. So using this we can share that what is the contamination level, what is the chlorophyll level. So if you want to show the chlorophyll level in water, what does it indicate? It indicates the health of the water. So using the different indices, we can use to show the various quality of water related to turbidity. So you can see that we have created a zone where blue is pure water, and as you go towards pink and red, that denotes the impurities in the water. So using this formula, using this indices, we calculated, we measured, we can show especially through various signatures, through various colors, that what are the different zones where the water quality is high, which are the area where the quality is poor. And such kind of analysis can be easily mapped and be shown using satellite images. So you can see this is a pre and post monsoon. So pre-monsoon, you see the water turbidity level is less, and post-monsoon the water turbidity level is high. This is because that during monsoon it brings a lot of sediment in water is there, that leads to a very high level of contamination level during post-monsoon, and during pre-monsoon all the water gets settled. So you will see that the major portion of the river lies under the loop what turbidity level. But when it comes to the post monsoon, the turbidity level is very high. So why physics and RT based model we are using? Because we want to see the spatial extension, the characteristics, the classification. Now we have mapped it, we have classified using satellite images, but maybe many times the people will say, I am not agreeing to your results. You are just making a false figure, you are just showing the false data set or false images of the area stating that the water quality is poor. So statistically you have to correlate all these data sets. So this is the various models that we'll be using in water quality index. The different properties like the models that are existing or simulation based is open or ocean case one. So you have got various models that are inbuilt, and you will be using it in your day-to-day activities and the laboratories when we'll be doing it. This is the statistical analysis, the statistical knowledge, how in different models the different particulate or different matters or different chemical properties of the matter behave line. So you see by simulation models you can see what are the different kinds of levels, the ranges, the contamination level. So all such statistical analysis has to be created whenever you are going for any kinds of water quality turbidity analysis, where you will be finding the water quality parameters, then chlorophyll concentration, then suspended sediment concentration. So this all optical properties will be connected to deep water reflectance, then this will be connected to reflectance just below the water surface, then we'll take the bottom there, then bottom albedo, a reflectance just above air water. So these are the various kinds of inland water color simulator. This is a specific software customized to know about the chlorophyll content in any water body. If you want to know the chlorophyll concentration, suspended concentration, what is the different. So you can see by using this combined combination and different combination, you can create a spectral response curve for those areas. So you can see how the material, if it is changed, the contamination is changed, the spectral response curve changes. So this is the another data where we have used the hyperspectral data sets, its latitude, longitude, its starting time, end time, what was the number of samples, line, bands. So if you use this hyperspectral data sets, you can create such graphical or representative maps showing the different odd features like chlorophyll concentration, CDOM concentration, SSC concentration. So using the color combination, we can have a standardized color combination for all the parameters, and you can see which are the zones which are having the high level of concentration, which are the zones which are having lower levels, and which are having intermediate level. So using this we can show what is the condition of water body, what is the condition of a wetland, what is the condition of various earth features in an area. So you can see that how the various samples has been collected from the field, and their spectral response curve of the same feature has been created, where you can see that the deep water, shallow water, coralline sands, mangrove sand, submerged sand, algae, submerged algae, silt, submerged silt. So various earth features are there, and you can see that each and every earth features behaves differently in different bands. If you go for the blue band, green band, and near infrared band, red band, you will see the maximum difference between the various earth forest or various earth features is highest in the near infrared band and the middle infrared band. But if you compare that with the blue band, you can see the difference is quite less. So if you are using only blue band, maybe you will not get the accurate amount of information. Even if for the green, in order to make the various or object differentiable, you can use red near infrared, shortwave infrared. So this is the water depth of that area. What is the water depth? So you can see which are the area and what is the depth, which is the area having low depth, which are the area having high depth. So using remote sensing and GIS, we can also understand the depth of the data set, where what is the depth, whether it is 2 meter, 5 meter, 10 meter, 20 meter below the water level, we can easily be calculated. Then the chlorophyll concentration, what is the chlorophyll concentration in this water, ocean water, can be calculated. Then suspended sediment concentration, SSC. What is the amount of sediment concentration in that area? Where is high, where is low? So you can see that majority portions in the ocean, the suspended sediment concentration is high. The same is for sedum. Then fractal coverage of sand, which are the areas, what are the ranges where the fractal concentration is high, where it's low. The same is for fractal silt, the area which are having a more than high, low, medium. So using color combination, you can show which are the area which are having algae. So using such study, satellite images provides you the various physical, chemical, and biological understanding of the terrain. So you can have a basic understanding of each and every area without going into the field. This is a case study, another case study where we have taken the three different parameters, three study related to three different locations. So figure one is remote sensing reflectance versus wavelength, how the different earth objects are behaving differently. And secondly is field photographs of lagoon water, Chilka Lake, Odisha. So we have taken the field photographs, and then we wanted to show which area is having high turbidity, which area is having low turbidity, which is having intermediate turbidity. So without going into the field, using the various indices and the models that are existing in the software, you can state away and directly state about the turbidity of the water condition in that lake, pond, or river. And that will be a great help to the society, because by knowing this, I can easily understand which are the zones that are having high level of contamination, Now my focus will be ki why this turbidity is only distributed to only this portion of land, whether that is natural or whether that is man-made. If it is man-made, what are the point sources which are creating those errors, and if it is natural, how we can naturally clear this water. Then what is the bottom albedo? By using the various remote sensing indices, we can collect this also about the bottom albedo. Then depth, where is the depth low, where is the depth high? Means the turbidity, I can say that if the depth is high, the turbidity is low. If the depth is low, the turbidity is high. Means maybe there is any relationship between the Sorry, there was some internet issue. So we have already seen how this remote sensing NGS will be used for such studies. And now we'll be using how the remote sensing NGS will be used for various kinds of cryosphere understanding, like glaciers. So the Earth's snowy and icy regions, snow and ice, they're very common, are known as cryosphere. So whatever glaciers, what you're seeing, will be classified under snows, will be classified under cryosphere. That is a broader term, or also known as the collection of both snow and ice. So, a word derived from the Greek krios, meaning cold. So, it was derived from a Greek word that says krios, meaning cold, and the constituents of cryosphere are thus. So, what are the constituents that comprises cryosphere? Are snow cover, sea ice, freshwater ice, that is frozen lakes and rivers, the large mass ice masses on the land like ice sheets, glaciers, and related phenomena such as ice shields, ice bore, and permafrost. So temperature on the Earth's surface generally decrease with the increasing distance from the equator. So as cryosphere is largely at a high altitude, and the altitude phenomena that we already know, that we have already studied. So what is the importance of cryosphere? The importance of snow and ice and snow on the Earth's surface is significant over a wide range of spatial and temporal scales. Locally and regionally, the cryosphere interacts with the human and natural environment in both positive and negative ways. Because we are talking about snow, glaciers, so that is having a positive and negative effect both locally and regionally. On a global scale, the cryosphere represents an important part of our climate system, because we are getting water, we are getting drinkable water, we are getting water for irrigation, that is cooling the monsoons, that all is possible because of these glaciers, because of this snow, because of these mountains. So that is very important for Earth system climate. Then ice and snow are generally highly reflective of the incident, that is shortwave infrared radiation. So they provide a feedback mechanism to the system, that is more cryosphere means that the Earth retains less of incident solar radiation. The more is the cryosphere, the less is the solar radiation. So their presence and annual and long-term variation modify the distribution and the flow of water. So if there is a change in the climate, what will happen? That will create an effect on the glaciers and snow, and finally that will change the entire distribution and flow system of water. That's why each and everyone is talking about climate change. So ISRO is conducting the various programmings on mapping and monitoring of these cryospheric resources and understanding the processes that are involved in cryosphere and hydrosphere. That includes snow, glaciers, sea ice, mountain glaciers. They are the various terminology that will be reading it in coming slides. So you can see that in the world map that approximately global distribution of snow cover on 1 degree sheet. So you can see what are the areas that are under various kinds of snow cover under throughout the area. So you can see this light shaded area. So that is very small in number. So the lighter gray shows the area where the snow cover sometime occurs, and the darker side shows where the cover is essentially permanent. Okay, where is temporary, where is permanent. So all such kind of understanding at a local level, at a regional level, can be understood using satellite remote sensing databases, because this terrain are those terrain that are inaccessible, they are unapproachable, and they are multi-dimensional. That's why you can see this because of the area, the environment, the connectivity. The remote sensing provides you better understanding of differentiation between snow, glaciers, ice, cloud can be done. So snow is defined as falling or deposited ice particles formed mainly by sublimation, as per the definition given by UNESCO and various other meteorological departments. So in this lecture we are concerned with snow cover rather than falling snow. So whatever understanding or whatever thing that we will be reading is the snow that is covered on the land rather than the falling snow that is falling. So we are concentrating more on the snow that is on the earth surface. Roughly 5% of the global precipitation that reaches the earth surface does so in the form of snow, although in Arctic region the proportion reaches to 50 to 90%. So the permanent snow cover is retained for many years. The latter occurs principally in Antarctica and Greenland, so that the great majority of permanent snow cover is in southern hemisphere phenomenon. Temporary and seasonal snow covers do not survive the summer. Typically, seasonal snow cover will survive for several months, usually being replenished throughout the winter, while a temporary snow cover survives for a matter of days. So, temporary and seasonal snow cover are predominantly in the northern hemisphere phenomena. The spatial extent of northern hemisphere snow cover, excluding Greenland, varies between 4 million square kilometer in August and 46 million square kilometers, roughly 40% of the land area in January. The maximum mass of water represented is 65 mm of water. So you can see the distributions of various glaciers throughout the earth. The dotted line are representative of Himalaya, then you've got Alps, then Andes, that is west of South Africa, south of equator, then glaciers of Rockies, west of North Africa, north of 38° north, then glaciers of China and Russia, then glaciers of equatorial Africa, then glaciers of Alaska, glaciers of New Zealand. So you can see the various location, and you can see that it is very few in numbers. The glaciers are very few in number if you compare throughout the globe. The area, the coverage is quite less. So what is the surface area of Antarctica is 13 lakh 58,630. So in the same way you can see the various surface area of various what glacial areas, but we are located, India is located in this region, that is 1,07,988. So you can see a very small area of land is under this glaciers area. So that's why we have to preserve these glaciers from melting, because they are the main source of water that is utilized for various drinking, irrigation, water quality, water recharge structures. They are the river system, they are the parents of the river system. If they don't leave, the entire river system will collapse throughout the world. So you can see that what is the area of Antarctica, 3.5 million hectares in square kilometer, Greenland 1.7, and rest remaining. So, what is the importance of glacier? The seasonal snow cover is responsible for the largest annual and interannual variation in land surface albedo and contributes an important feedback mechanism to global climate change system. Another important climatological effect is the thermal insulation provided by the snow cover, which reduces the exchange of heat between the ground and the atmosphere. That helps us to maintain the heat. At a more local level, snow cover is important for its potential for water storage for drinking, irrigation, hydroelectrical power generation, and for production of flood water. So you can see a large feature that is utilized locally. Then thermal insulation provided by snow protect plants from low winter temperature that provides heat. Snow cover also provides economic benefit through winter recreation that the tourists will be going, they'll be enjoying. So, because of the ecotourism, a lot of money will be generated, as well as it has got adverse economic impact through its potential to disrupt road and railway transport. So, it has got the merit, it has got demerit. Many times it will damage, it will wash out the road, dams, or maybe the tunnels. So there are snow-fed glaciers. Snow can cause avalanches. Recently in Uttarakhand, there was a avalanche that created or broke down the entire hydropower that was situated just below that avalanche area, and that led to loss of life, property. There was a huge loss. So you can see this snow how it looked like. So whenever we are talking about remote sensing, we are talking about this data sets what we are seeing. So you can see the videos. Can you see the figures, the slides?
Yes, sir.
Okay. So you can see that it's a very tough terrain. You have to go into the field because remote sensing fine. It provides you the data set. It provides you the information. But at last, you have to go into the field, and then you have to have a basic field understanding, and you have to collect the data sets using various instrument that yesterday we have already covered. Ki how spectral radiometers uses the spectral channel to identify the various art features. So here is a field photogram showing the spectral radiometer of snow in a spectral channel from 350 nanometers to 2500 nanometer. That was in the month of June 2009, taken by ISRO scientists. They have worked in a large projects, and they are working parallelly for not only Indian glaciers but for the glaciers that are throughout the world. So you have got Indian researchers are also working on Antarctica. They are also working on various other regions of glacier. They are showing their expertise. They are making those person trained in various instrumentation, technology, modeling, because this is a feature that involves a lot of field measurement is required, a field knowledge is required. The terrain is tough, so a person with a strong heart, commitment, of physical fitness can only reach to those spots where the field verification or the field data has to be verified. You have to have proper shoes, proper clothing. You have seen ki how proper instrument clothing have each and every scientist who are going to the field. They are wearing it. They are calculating. They are calculating the in-field data sets obtained from various instrumentation, and then they will be calibrating it. They will be validating the satellite based results. They will be calculating the accuracy of the models that they have generated, ki how accurate their model is, or is there any possibility of changing the model calibration. So you see this is a inaccessible terrain. The scientists, the ISRO scientists, and some of the professors of India who are associated with ISRO, they go into the field. This is a very tough terrain by seeing that there is no what I have already stated day before yesterday, that you will find no MACD, you will be finding no dominoes, no houses. You have to construct the tent houses will be there. The drinking water, there will be, you have to directly drink those chilled ice water, and there will be no person for help if you're feeling sick. So this is a very tough terrain to be working in the field of remote sensing, because at last you have to go into the field, you have to see the various changes that has happened over the decades, whether that is pertaining to geology, geomorphology. There is no road track, there is no railway track, there is no pathway that you will be taking those road or pathway and you will be reaching to your destination, and that is very far from the places where you will be last dropped from your vehicle. So many times the scientists have to travel 40 to 50 kilometers to reach their destination, and that is far away from the city. They have to prepare their food, they have to carry the equipments, they have to carry their food, they have to carry all the heated materials that are required, because this is a area that will be very cold enough. So working in the field of remote sensing, especially when you're working in glaciers and snow, is not a easy task. So you can see that how the various kinds of snows are there. So snow, ice, and glacier are the most interdependent, or many times they are used synonyms, but they are not synonyms. They are a different. Just like there is a catchment, watershed, basin. Many times we say a person not from that field will be saying disaster, hazard, vulnerability risk, all are different. In the same way, when you're saying glacier, snow, ice, all are different. You'll see the density. So what are the glaciers? So glaciers are the mass of snow and ice slowly moving down a gradient. They are slowly moving down a gradient, and snow is a porous and permeable aggregate of ice crystals. So whatever ice crystal that get deposited, when fresh, it appears bright white. So snow undergoes rapid changes in the grain size and shape with the changes in the liquid water content, temperature gradient. So snow, when it is densified, it becomes ice. Snow, when it densified, you becomes ice. So we do play with fresh snow. If you are into some tourist destination of Manali or Dal Lake in Kashmir, or other hilly terrains of India, but you cannot play with ice, because that is very dangerous, and you get a cut that can be a life threatening, can lead to infection of your hand, and that is because the change in the state. So you know what now the difference is between a snow, glacier, and ice. So, what are the remote sensing technique? How it is applied? How do we do the various kinds of analysis related to remote sensing? So, what are the properties of remote sensing of snow? The most important type of imagery for these applications are optical imagery that uses the infrared. In the visible near infrared region, snow has got a very high albedo, while the optical system can achieve much higher spectral resolution. They are limited to daylight and cloud-free conditions. So passive remote sensing imagery, snow has a brighter temperature that has significantly lower than that of a snow-free ground because of volume scattering in the snowpacks. So synthetic aperture radar is being also developed as a method to differentiate dry snow. Passive microwave systems can be used at night and through cloud, but their spatial resolution is coarse. A problem common to all approaches to remote sensing of snow cover is that much of the world's seasonal snow cover occurs in forested area and complex landscapes. So you can see that what are the changes in snow reflectance as the snow converts into the ice. So you can see how the dirty snow will be seen in blue, green, red, near infrared, thermal infrared. Then glacier ice, how you will be seeing a very high reflectance in the blue band as well as in green band, red band, and gradually in the near infrared band it is coming downwards. If you go for the fern, that is equally high, it is more than the glacier ice. And finally the highest reflectance is for the fresh snow, that is near about 1% in fresh snow in blue, green, red, near infrared band. So if we are using this bands, blue, green, red, near infrared band, we can easily identify the different forms of glaciers ice, dirt glacier ice, using the spectral response curve of various forms of snow. So you can see that how this snow we have already done key how the because the grain size are different, so that are being sensed differently in different satellite bands. So snow has got very high reflectance, at least for wavelength below zero point 0.8 micrometer. It is comparatively easy to detect against a background of snow free terrain. At the most basic level, single band imagery can simply be threshold to discriminate between snow free and snow covered terrain. However, the choices of suitable threshold value is not always straightforward and ancillary information is needed. The threshold may depend on the local imaging geometry, since surfaces that face squarely towards the incident solar and radiation will reflect more light to the sensor than those that are originated or oriented more obviously. A further disadvantage of using single band imagery is potential for confusion introduced by cloud cover. So the most common portion and the error that you will be seeing, that many times the you will be getting confused with snow, then cloud, then glaciers. So spectral reflectance of snow cover and of cloud are very similar at wavelength below 1 millimeter. They diverge in the near infrared to achieve a maximum difference at a wavelength between 1.55 and 1.75 micrometers. So the use of two spectral bands allows for a correction of topographical effect referred to the variations in the relative sun ground surface sensor geometry to change and sensor radiations by same factor in all the spectral bands, so that the ratio of measured reflectance or radiance in two spectral bands will be unaffected by the geometry, and the ratio is not in the fact that most convenient quantity to define, since it can in principle take any value between 0 and infinity. So if you want to see or differentiate glaciers from ice or a snow, by seeing a satellite image, anybody, this is a standard false color, or you can say a natural color. You are seeing uh, you will be seeing snow in blue color. Now, depending on the height, depending on its condition, depending on the topography, I can now easily differentiate the areas of glaciers in the Tibetan plateau. So their different color, tone, textures are different from the satellite images. So if we do identify them, we can identify the glaciated area. So you have got different band combinations that are available. So now we have to identify snow. Now we have to identify cloud, and then we have to identify no non-slow using satellite images, because they are the common feature that always you will be have to find. So by seeing the satellite image non-snow areas, it's very easy to understand, and because of their reflectance, they are obviously they are giving the darker reflectance, so they are the non-snow. And the area that are snow shows a brighter white reflectance, but cloud do have the white reflectance. But you can see here the cloud area, the color is different from that of a snow area. So you can see here also. So once you identify this features, it was just previously when you were seeing a satellite image, all white was like snow area, but now you can see these clouds. Once you've identified there are a lot of clouds in and around this glaciated area. Here also you can find the clouds. Rest are the non-vegetated area. So this is how it looks like in blue band, this is how it looks like in green band, this is how it looks like in near infrared band, this is how it looks like in middle infrared band. So you can see that in each and every band the glaciers are recorded differently, the grounds are recorded differently, the snows are recorded differently. So using the false color composite, what the band combination that we were seeing independently now will be used to create a false color composite in order to differentiate between fresh show and the cloud cover. So you can see that when we have used a false color composite of band combination, that is a Landsat image, when we use the band combination of 432, it was tough to differentiate between cloud cover and snow. But when we used the band combination 5 through 532, it was very we it was easy to understand because there is a difference in tonal variation, so we can identify that which are the area under snow and which are the area under glaciers using various band combination. So whenever you're working in glaciers, the band combination you have to see the foreign cover, the season of the satellite data that you're taking, all such features has to be seen, has to be verified. Then glacier inventory has to be done. So the common inventory means you have to identify the snot area. Where is the snot? Okay, now we'll learn what is snot. Then in this snot, you will be seeing that there is moraines, dam lakes have been created. These are the moraine dam lakes. Then you have got lateral moraines are there. Then ablation zone is there. Snow line is there. Glacier boundary is there. So all see differently. Then accumulation zone is there. Tributary glaciers are there. Lateral moraines are there. So this all are various geological features, various terms that are associated with geography, geology, or geomorphology. So generally, this all terms till now we have generally never seen how it looks into the field. Generally, you must be seeing in some books, but how physically it is seen, how in a satellite image. So you can see that each and every object and each and every term, each and every definition, what we are stating, if you see carefully, each and every feature has got some certificate or got some certificate key or has got some specific characteristics or has got a specific shape and size. So once you know how ablation areas look like, how lateral moraines look like, what is snow, how it look like, what is snow line, so it will be easier for you to differentiate the various kinds of snow area, then snot, then ablation zone, then accumulation zone. So accumulation all where the area where the glaciers accumulate, and where there is a detrition, there is lot of deformation, or it is in the form of ice, you can see, or there is a melting process going on, that will be converted, or that can be said as ablation zone. So we'll be reading in detail in coming slides. So not only by using visual interpretation or various keys to identify the various odd features, we'll be using the band restoring technique that I have already stated you, that normalized difference snow index to differentiate between the snow and the other odd method, and the formula is green minus shortwave infrared by green plus shortwave infrared. So snow is normally assumed to be present if the Ndsi exceeds a value of zero point 0.4. So if the although recent work has suggested that optical value of the throws values varies seasonally. So there cannot be any fixed value stating ki at what value will be saying ki you will be finding snow. That depends on image to image, that depends on season to season. So we have created this NDSI method for snow cover mapping. Here you'll be seeing ki when we are creating a scatter plot of the various earth object, you can see ki how differently rocks, vegetation, water, fog, clouds, snow, they behave differently in the various spectral graph that we are creating. So not only the optical remote sensing data, the microwave remote sensing data like SAR has got a great advantage for microwave for delineation of snow glaciers. So advantage is of high spatial resolution. SAR data has got a higher spatial resolution, is insensitivity to cloud, it's an operability at night, you can operate that at night, but the relevant electromagnetic radiations are complicated. The attenuation length of microwave radiations in cold dry snow is large, and this kind of snow is therefore transparent and hence invisible to radar unless the snowpack is very deep or at radar frequency above about 10% gigahertz, which are normally not commonly used in SAR imaging. However, when the liquid water of snow exceeds about 1%, the attenuation length is reduced to few centimeters, and the radar backscattered is usually dominated by surface scattering. However, the questions of whether such snow can be differentiated from snow-free terrain depends on the geometric and electromagnetic characteristics of the snow cover and snow-free terrain. Various studies have demonstrated that wet snow cover can generally be distinguished from snow-free terrain. The discriminatory ability increases with the frequency, so that observation as X bands are preferred, although C band imagery is equally adequate. So you can see how this radar set is used for mapping. On the right hand side, you will be seeing optical satellite image, and on the left hand side, you will be seeing microwave satellite images. You see the same feature how it has been seen on the optical data and how it is seen on the microwave data. So you will be finding that the microwave data, when it comes to uh, this snow, glaciers, ice mapping, melting, composition, delineation, they are having the more capacity, more capability of identifying the various earth features. So using this microwave remote sensing data, we can detect the lake buried under snow. There is a lake that lies below the snow. The detection of glacier ice buried under snow, then detection of old snow buried under snow in accumulation zone, and finally detection of probable crevasses zone buried under snow. So such kind of geomorphological features can be easily identified using microwave remote sensing. Nowadays we are using hyperspectral remote sensing, where snow cover often occurs in the area of complex landscape. For example, including areas there are forecasted as clear of tree. At coarser spatial resolution, the problem of mixed pixels increases. One approach to solve this complex landscape is use of spectral mixture modeling, that is called spectral unmixing of imagery with a sufficient high spectral resolution. So we have used average where 224 spectral channels between 400 and 24 60 nanometers. So this technique consists of identifying pixels in the image representing end members that are believed to be representing the homogeneous land use land cover time. The reflectance spectra of this end members were determined, and other pixels in the image are assumed to consist of linear mixings of this pure land cover types. So you can see how the various earth features behave differently in hyperspectral analysis of snow. So those features will be used for identification. This is also used for energy balance approach. In this method, various energy exchange such as radiation and turbulence is determined. This normally needs data on incoming long wave and short wave radiations, snow albedo, wind speed, humidity, temperature. Such data is difficult to get, but it is not difficult to use. Then we can use for degree day approach, or temperature index approach is mainly based on air temperature and other meteorological data. Air temperature is the most commonly used index. The degree day method is more popular because temperature reasonably represent the energy flux, and at the same time it is relatively and easy to measure, explore it, and even probably forecast. So we can do the various kinds of energy balance calculation using the snow melt runoff. So we can take out the snow melt runoff is what is the total amount of snow that is coming out as runoff because of temperature, because of precipitation. So all such calculation, all such method, all such operations can be easily mapped, monitored using satellite remote sensing. So you will be seeing that the ISRO is regularly updating and mapping the snow cover atlas of various river basins of India, and they are customizing it. What are the accumulation zone, what are the ablation zone, whether the area is increasing, decreasing, what is the characteristics of northern Himalayan glaciers, what are the characteristics of central Himalayan glaciers, what are the characteristics of northern Himalayan glaciers, whether there is any change in the temperature pattern of any of the glacial types that we are searching it, or whether we are mapping it. So this kind of variations can be easily mapped over the various dates using satellite remote sensing data sets. So you can see here how different algorithms are used for mapping of this various snow cover area. So this is the formula that we'll be using for getting the snow and glacier melt off runoff model, where we'll be calculating all the seasonal runoff, glaciated rains. So all has to be calculated in order to get a understanding of the terrain using satellite data. Not only satellite data, temperature data, altitude data, rainfall data, basin area, and all will be taken into consideration to create the total amount of runoff that is created from the precipitation. And finally will be this running this data, and the different glaciers model will be generated. So the different the inputs for this models is hydrological season. You have to provide the snow area and coverage, altitude, then glacier area and altitude, then average seasonal degree in temperature, average seasonal data, then melt factor, runoff coefficient, all has to be calculated. So what is the input and output parameter of this model? Average altitude, Then temperature rose, mean of aerial extent in different months, then mean runoff, then model stream runoff, then what are the various parameters. So you can see that each and every area is divided into grades, and then these grades are representing the various topo sheets, and those topo sheets are variously subdivided to get this glacier runoff model. So they have got a limitation. The basically limitation is runoff is estimated seasonally. So you can see that how these different models are calculated and implemented. So you see this is a case study of Parvati River Basin of Himachal Pradesh. What is the height? What is the area? All has been mentioned. Then what are the satellite image we are using? A-Waves Lease 3, then Aster to calculate the distal elevation model at 30 meter, then Ndsa to differentiate between the snow covered area and cloud cover. Apart from that, we are also using the meteorological data like temperature, elevation of meteorological station, observed runoff coefficient, then precipitation, discharge data for validation. So all such data sets will be taken into consideration to calculate the temperature, precipitation, melt factor, elevations. All such parameters will be calculated from this formula, and finally will be generating the grid layers of Parvati Basin. What is the map that was generated from Ndsa? How is the maps look like when we create a distal elevation model of that area? So what is the temperature area? All the runoff coefficient is calculated. Then we'll be simulating it. We'll be seeing the accuracy. What is the accuracy of the discharged or of the that we have created or what we have generated. So all will be verified through various statistical model in the field, and then we'll be creating the different kinds of hydrograms in that field. Finally, we'll be creating a energy balance approach to get a final map of that area. And with this, I'll end my today's presentation. And now you can have a basic understanding of the snow, how the remote sensing GIS technique is used for snow, why we are using microwave data sets, what are the advantages, what are the disadvantages of microwave data sets, how you are going to classify the data sets, how will you differentiate between snow, glaciers, ice, what is the difference, property difference, and finally how the satellite image is used for mapping and monitoring of this glaciers. With this, I come to end of my today's presentation. We'll be joining tomorrow. Meanwhile, we'll have 10 minutes of group discussion and final quiz in your LMS. Thanks for joining.